Okay, so welcome everyone, and a great welcome to our guest speaker today, Professor Francesco Pegoraro, to the IEEE second presentation series on nuclear energy. It is really a great pleasure and a great honor to be the first moderator of the second presentation series in nuclear energy, or the first talk. So before giving the stage to Professor Pegoraro, who today is going to talk about fusion energy, possible scenarios of its long-term impact and public perception, I would like to share with you a few slides on the series. So first of all, there is really a need for clean, sustainable energy. And as Ban Ki-moon said already in 2014, energy is the golden thread that connects economic growth, increased social equity, and healthy environment. Sustainable development is not possible without sustainable energy. So there is a global energy system transformation, and we are really seeing a lot of it even on everyday's news today. So the IEEE presentation series on nuclear energy is brought to you by several entities within the IEEE. You see here a few. The IEEE Vancouver section, the IEEE Future Direction, the IEEE SASTEC, IEEE Nuclear and Plasma Sciences Society, IEEE Standards Association, and IEEE Planet Positive 2030. I am Cinzia Davia, by the way. I'm a professor of physics at the University of Manchester, UK, and Stony Brook University, USA, and I am a member of the IEEE NPSS. So what is the presentation series on nuclear energy? This is intended, in fact, for a broad audience, not only engineering or technical community, but it is also intended for industry, regulator, policymakers, community stakeholders, etc. So it's also intended for the general community with an interest in the energy transition or in clean energy and energy alternatives, nuclear reactor technology and related topics like the ones that we're going to be listening to today. It's also going to be serving the needs of the profession and the public by increasing awareness and understanding of nuclear technology. What you see in this slide are a set of links that could be of interest to you. They are going to be posted on the chat, so don't worry. You will have an opportunity to see the link to the series web pages, to the presentation series, and so also have access to previous presentations that could be of interest to you, and to other on-demand presentations. Next talk that is going to be broadcasted the 28th of January 2026 is going to be presented by Dr. Laura Ravasi. So she is a physician, a scientist with more than 20 years at the interface of nuclear medicine, radiopharmaceutical R&D, and global commercialization. She is bridging the very interesting and delicate link between clinical academy and industry experience to support innovative diagnostic and theranostic from discovery to patient access. She's going to tell us about personalized medicine with custom-made radioisotopes through small modular reactors in the near future, science fiction or reality. But going back to today's talk and the presentation of Professor Francesco Pegoraro on fusion energy, possible scenario of its long-term impact and public perception. So first of all, let me just say a few words about Francesco. So his research really covered in different aspects of plasma physics, the nonlinear dynamics and applications, ranging from the physics of controlled thermonuclear fusion to magnetospheric and solar plasma, and the relativistic plasma produced by the interaction with matter of very high intensity laser pulses. So he is the author of more than 400 papers published in international referred journals. So today, Francesco will tell us about the state of thermonuclear fusion research, noting that scientific and technological progress makes commercially viable fusion by mid-century plausible. However, there are key uncertainties remaining around cost, investment needs, and the social, political, and geopolitical impact of fusion, including which countries will be able to access it. So we will stress the need of clear and accurate information to address public and political misunderstandings, especially as the world risks reverting to fossil fuel dependence. And we saw that on the news very recently after the last COP meeting in Brazil. But I will just stop here and pass the floor to Francesco Pegoraro and welcome him on this nuclear series, second series on nuclear energy. Francesco, the floor is yours.
Thanks very much for the presentation. Now I'll share my screen.
And while Francesco is doing that, I forgot to mention something very important. Please post all your questions that will be addressed at the end of the presentation on the chat, or on the chat of the Zoom platform. Thank you very much.
Do you see my presentation, my first slide?
Yes, Francesco.
Perfect. Okay. Good morning on the Pacific coast. Here it's already evening. And thanks for inviting me. And I will talk about nuclear fusion, but not so much on, as was mentioned before, on its technical aspect, but mostly on its possible long-term social impact and on the perception that the public has on nuclear fusion. Here there is a very recent article on public acceptance of fusion energy in Europe. It's just this year, 26. And it shows that, I will come back to this point, that the acceptance of fusion grows with the knowledge of what actually nuclear fusion is. And this shows how important it is to clarify to the public what's the difference between fusion and fission and what are the problems or the advantages that nuclear fusion can bring to the energy market. So let's be very simple to start with, and to show, just to stress the important difference between fusion and fission. I mean, fusion, you have two light nuclei, for example, for, in this case, deuterium and tritium, that fuse together and produce an alpha particle, a helium nucleus, and release a neutron, and the energy it shows in the figure. Well, what is important is that these reactions can go on, can spread, just because of the energy present in the medium that is carried by charged particles that will be present. And there is no chain reaction. That's the main point. But on the other hand, you have to confine an ionized gas for a time that is long on the characteristic time of the nuclear reactions. Fission, on the other hand, is different because you start with heavy nuclei that get split, and fusion is propagated by neutrons that are released by the previous fission events. And in this case, you can have a chain reaction. Well, you need a chain reaction that does not occur in the case of fusion. Well, let's start with a little bit of history. The effort on thermonuclear fusion has, has a long history because it had always had a dual role, because in a sense it is a destructive force that powers the hydrogen bomb. It is, on the other hand, it may contribute to solve the growing need for energy that is one of the main causes of conflict among humankind. And historically, fusion research has promoted international collaboration and has been an instrument of peace. And I would hope that this remains true even when energy production is finally achieved. And quoting from an old paper of Werner Heisenberg, when the fire of the star is brought to Earth. However, bringing to Earth the fire of the star has proven difficult. Physical processes that occur in fusion energy in a laboratory and in a star exhibit strong differences that derive from the miniaturization that is needed in order to go from stellar to laboratory dimension and to ensure that the energy is produced in a controlled way. Well, and this miniaturization changes completely the physics, because you go from a system, a star, that is electromagnetically opaque, it's a dense system, generally at local thermodynamic equilibrium, to a thin system that is electromagnetically transparent, with a dynamics that in general keeps the plasma far from thermodynamic equilibrium. And these miniaturizations require that you must have higher energy particles in the laboratory than what you need, for example, in the sun, and more efficient nuclear processes, essentially deuterium-tritium or deuterium-deuterium or deuterium-helium-3. And now people are also interested, but there are some problems in proton boron 11. Well, these difficulties in achieving net energy production have been the main stimulus for a strong collaboration in international collaboration that is quite a miracle, has lasted through more than half a century, through the Cold War, and possibly even now through the tensions due to the war in Ukraine and in recent years additional tensions. Well, this collaboration has started quite a long time ago, and it has been endorsed at the conference in Geneva in 1958, the second conference on the peaceful uses of atomic energy. And I'm quoting here from Lev Artsimovich, who was one of the greatest Soviet scientists in fusion, that the problem of fusion seems to have been created especially for the purpose of developing close collaboration between the scientists and engineers of various countries. Well, a number of years has passed from that time, and there have been important recent positive results. I will not go into the details, but both in magnetic and inertial fusion, I will comment in a few slides what's the difference between the two. There have been the very important result in inertial fusion at the U.S. National Initial Facility in December 2022, where for the first time there has been an ignite, I mean, the deuterium tritium, the deuterium tritium pellet has ignited. And also magnetic fusion with different emphasis, there has been a very important result at the Joint European Tokamak in again December 2021, where almost 60 megajoule of fusion energies were produced. Well, what is just a brief reminder, what is magnetic fusion, magnetic confinement, and what is inertial confinement fusion? Well, the point is that you need, as I said, extremely hot gas, completely ionized. Is actually it's called a plasma, more than 10 kilo electron volts, 10 million degrees. And this cannot touch any material. The plasma would be cooled immediately. So you have to confine it in two ways. One is the magnetic field, and for topologic, for a number of reasons I don't explain here, it has to be confined in the best way to confine it at the moment is in a toroidal configuration, kind of not donut. The one shown here on the left that corresponds to what is generally called a tokamak, and on the right-hand side you see the picture of the internal chamber of the jet tokamak. On the left is just the chamber with the tiles of graphite, no plasma. On the right there is a small insert with a plasma seen in the optical ranges. What is interesting is that at this temperature you don't see the plasma, you just see the cold part of the plasma, top and bottom, where you have line radiation because the plasma is not fully ionized. Inertial confinement fusion is not actually confinement. What you do is you shine a pellet of deuterium-tritium with very powerful lasers, and you can do it in two different, and the pressure of the laser, and most importantly, the pressure due to the ablation of the pellet compresses the mixture of deuterium and tritium and brings it to the conditions, temperature and density needed for producing energy. And you can do it indirectly with the X-rays produced by shining a capsule of gold generally, then radiates on the pellet, or just shining directly the laser pulses on the pellet. There are advantages and disadvantages of both systems. Well, the recent result was in indirect drive. Well, but it's not only just this experimental result, it's the spread of the interest in fusion all over the world that has been very important in the last 40 years, and just becoming even more important in the very last decade. And there has been advantages in science and technology of magnetic fusion in countries outside Europe and the US, and in particular China. I will come back to this point, Japan, India, and Korea. From the physics point of view, also, there is another very interesting and important development, that is the renewed interest in high magnetic fields up to almost 20 Tesla. And this interest has been rekindled by the recent realizability of large-size, high-temperature superconducting magnets. And this is also important if one wants to discuss a connection between fusion and other application, for example, medical application. But there is a word of care, and that these developments do not guarantee that it's really, we can expect really a significant shortening of the time required for the realization of commercial nuclear fusion plant, not just an experiment on the prototype, something viable on a commercial side. And there is a very famous, well-known international experiment, international thermonuclear experimental reactor, ITER. And at the moment, the first deuterium-tritium operations is not expected earlier than 2039. Well, what is the present state of magnetic fusion? I'll go very short on this, otherwise I will not have time for the rest. But although most of the I'll take it from this article by Ambrogio Fasoli that is very clear on this subject. It's an extremely interesting article. And although many fundamentals are well known today, there are still a number of gaps in our knowledge. The best plasma scenarios in terms of temperature and density to reach how to get out the particles, the ghost, the alpha particles and the heat in particular from the chamber, how to deal with plasma transients, disruptions in particular that could damage the structure, then to study what has not been really achieved up to now. It's a burning plasma regime where the alpha particles that are produced by the fusion reaction are the main source of heat. So they can take the role of the external heating and bring your experiment to a condition that is self-sufficient. There are technology gaps, for example, in particular, real-time control. There is problem with tritium breeding. I mean, tritium is not largely available in nature, so it has to produce. And, well, it is radioactive in the case. And the technique is to have a blanket of lithium in particular, where the neutrons produced by the fusion reaction, by spallation, produce the tritium that you need and for going on with the fusion reaction. That's a problem with the materials, with magnets, but a point that is stressed in Fasoli's paper is that the most formidable challenge for achieving fusion energy does not derive from any of these physics or technologies issues, but rather from their integration into a reliable, available, long-lived, and economically competitive power plant to put them together. Several issues from the point of view of inertial fusion. Well, several issues like tritium breeding are very analogous, but there are problems that has to be solved that are still characteristic of inertial fusion, even if ignition has been achieved. For example, you must increase the target gain. So the ratio between the energy you get and the energy you put. The repetition rate has to change, not just a few shots per day, but 10 hertz. Then the efficiency of the lasers, okay, have to be increased. Target manufacturing has to be rapid and less expensive. And okay, standard problems like how you inject this target pellet in the chamber and how the problem with material, how the reactor chamber can survive the neutron flux. And there are a novelty now in the last 10 years, and is a role that artificial intelligence seems to have as a major player in both magnetic and inertial fusion research, reformulating the decades-old effort in numerical simulations. I mean, the physics of plasmas, for fusion plasmas, the aerodynamics is so complex that that is not possible to understand it completely on an analytical basis. You have to construct models. But from the point of view, the potentialities of artificial intelligence can be very promising, both from the point of view of control of of your experiment, but also for understanding what is or modeling modern understanding what is the physics and the dynamics of your plasma. And there is this recent press release and modeling a star in a jar in second. This is British humor. Jar goes represent the strange shape of the experimental configuration they were presenting. And I can read scientists have developed a tool, an artificial intelligence tool, which can simulate complex fusion plasmas in seconds. And this can really change the path to this design of future experiment. But a point that has been quite evident in recent years is the need for a faster track. Periodic revisions toward longer times of ITER, and also the realization that it might be safer to have a wider approach and search for other difficult, rather different possible approaches to achieve energy production, not just with the tokamak, for example, referring to magnetic fusion, has shown the need to proceed at a faster pace. And new projects were started recently aimed in a number of cases and addressing specific scientific or technical issues, not the whole picture as it was characteristic of either project that wanted to solve all problems from ignition to technology. But there is a change that most of these projects are not anymore international. They are conceived at the national level. Look at, for example, STEP in the UK or BEST in China. But at the moment, international collaboration continues to play a role, at least with the exchange of scientists. And if you think about a faster track, China comes into the play. Because in the last 10 years, China has taken a dominant role in fusion research from the points of view of investments, results, fast schedules. And the risk is that these developments are making work in Europe or in the States obsolete. I mean, that may be my point of view, but I think it's really a major player, new major player in the development of fusion. And this was presented in a very polite way, but quite clearly at the IEEE Fusion Energy Conference last October in Chengdu. And something that was to be noticed is that for political reasons, no scientists from USA were present at this conference. Well, there is another also important kind of change that occurred in the last 10 years mostly, and it's the recent developments in fusion and research has been the entry of a large number of private initiatives, or at least partly private venture capital in some sense, in the form of startup companies. And there are quite a lot of initiative, both in inertia and magnetic fusion. And this reflects a process that is already evident in other fields of technological innovation, where the role of governmental or international structure is taken in part by private ones. And here I cannot go through them, but there is a list of some of the most successful of these startup companies, the ability to collect money and the comparison between the funds they obtained and the cost of other physical endeavors like the Large Hadron Collider or the space station. Well, some of these companies look a little bit strange on a physics problem, but some of them, a few of them, are really valid, and the initiatives, I mean, they are innovative, and their this initiative will certainly have an important role in support and stimulation of fusion research. I mean, even if they don't solve the full problem, they certainly will speed up the development that we have seen at the beginning of this century. Well, here there is a list of companies, and what and not only and the number of companies not directly involved in fusion, but for example in fossil fuel like Chevron, Shell, and other are financing these startups. So there is a large influx of money, and something quite unexpected, at least for me, happened a few days ago, where Trump media plans to merge with the company in California with a $6 billion deal. Well, the division between private and public is not always sharp. For example, while also it's clear from the DT consortium in Italy, which is a large tokamak that is being built in Frascati, close to Rome, but also, for example, in particular in Germany, in inertial fusion, where there is a large investment from governmental funds. Well, I'm repeating myself a bit, but these startups can really represent an opportunity to show in a shorter time that a net energy source based on nuclear fusion has actually been achieved, and possibly to indicate alternative approaches in the event that the current one, based largely on tokamak, doesn't appear to be optimal, doesn't turn out to be optimal. Well, recently there has been an additional change, as far as I understand, and it's a public-private partnership, this G4 go for fusion. And what is the point is that some of the best of these startups are were funded by scientists coming from big laboratories or universities, bringing with them their know-how. So now there is the idea in this Go for Fusion initiative that is very recent to put together the freedom that private companies have and the amount of money that they can collect, with the knowledge that the best startup have in the form of personnel that had been working in well-known and successful public or university endeavors. Well, what is the point now? What are the returns at the moment? At the moment, even it is clear, at least in my opinion, but I think it's actually true, independently of what some of these startups say, that commercial fusion reactors, not just experiment igniting plasmas or prototypes of fusion reactors, will not be able to supply power to the electric grid for at least 40, 50 years. Think that you don't have to just to build a single fusion reactor. You have to build quite a number of them in order to be available on a worldwide level and be really a contributor to the electric power on the grid. Well, even if there is still this time expectation, not for the realization of an experiment, but really for the realization of an energy source based on nuclear fusion that is widely available. Well, people have understood that nuclear fusion may represent a viable solution to the problem of energy transition. In this perspective, separate countries, as opposed to supranational institutions and possibly also large companies, already aim to capitalize on this future source of energy, and in the meantime, in its returns in terms of technological developments and applications, advanced materials, high temperature superconductors, that are important, and as I said, for medical applications. Well, and this is also seen from the point of view of the companies that have been suppliers to the research in fusion energy by constructing pieces for these big tokamaks and so on. And now they are asking for greater participation in projects, not just building pieces of experiment, but also acquiring the technical and the management expertise that will be used in the commercialization phase of fusion energy. So this is quite a change, and it shows that the number of countries, a number of companies are preparing themselves for an economy that is not immediately available, but will be available based on nuclear fusion. And as I said, the construction of quite a number of reactors that will be needed to feed the grid, well, that will require quite a lot of technological and scientific knowledge in these companies. Well, let's go to public perception and the history of the development of nuclear fusion as a world energy source has made it clear that public acceptance plays a major role. This is quite evident in a country like Italy, where fission energy had a very difficult life. And so this is the public perception is something we have to really take into account. There is a problem that public opinion does not discriminate clearly between fission reaction based on obsolete technology and new safer design. And often this is clearly for fission. And very often the information is more ideological than factual. But so we have to be clear that we have to explain what are the real dangers and to distinguish if there are and to distinguish them for perceived dangers of fusion energy. Otherwise, this will be a problem. And there is a literature on this point that we don't need just to be approved on a scientific point of view on the safety, but also we need a kind of social license. Well, but the perception is mixed, at least from my experience. Public perception is dormant. Even the basic difference between fusion and fission is very often not well understood, even if this information is quite available on the web. On the other hand, in recent years, published by the reverberation in the press of recent fusion results, public interest in fusion energy has certainly increased and expectation, more or less justified, are high. What is also the relationship between research in fission and research in fusion? Certainly, fission and fusion development may have been conflict in terms of involved economical and political interest, even within a market still dominated by fossil fuels. But one should look at this problem differently because fusion can learn a lot from, I'm quoting here, from their atom splitting cousins. It's not one way or the other. Collaboration will prove to be beneficial to the success of both. And here I'm taking from a document of the International Atomic Energy on possible synergies. For example, fusion materials, fusion controls, development of codes and so on. But let me go to the last part of my presentation. Let's start from a question. Are we turning towards commercial fusion? As I already mentioned, private capital is joining and possibly even taking the place of public capital in several new research initiatives. And international collaboration may leave the field to national initiative. And this is possibly in tune with the present wave of the globalization. But these changes will not be for free. They will come at a political and social cost. Well, essentially, deuterium and lithium, the fuel finding that you need at the end for running a deuterium-tritium reactor are geographically widely available. So that should not be the problem. Even there is something called green economy where rich nations produce energy, but the materials needed are mined in poorer countries. But what is most important, in my opinion, is that development and the construction of nuclear fusion reactor will have huge investment costs and will likely to be affordable only by rich countries. And not only money, it will require technical know-how. And this will also be available only in countries with a strong scientific and technological tradition, or in countries capable of buying it, obviously. There are two consequences. First, that scientific education will be fundamental for the well-being of a nation. And, and a slightly negative one is that it seems unlikely, at least to me, that fusion energy will be a source of energy available equitably and affordably to all humankind. Well, the international social and political impact of fusion has not been at the moment fully assessed, and this is an important problem, in my opinion, to address. Which country will have the concrete possibility of accessing fusion in terms of investment and of expertise? And the problem, could it simply be that with different players, the present control of energy access by powerful nations and so on still will still continue even after thermonuclear energy on a large scale in order to feed the grid is developed. So let me conclude now with a few points. First one, there are compelling arguments that thermonuclear fusion could represent the long-term solution to the problem of decarbonization in the energy production. What is important that it will represent a solution that does not require reduction in social or economic standards. And because this seems to have created, as far as I understand, a kind of negative reaction. I mean, the kind of reduction in social and economic standards seems to have produced some worries recently in the reaction of the populations, of the public. Then what is important is to bring clear and honest information, because there are misunderstandings, both at political level and at the public level, about the timing and the implication of the implementation of fusion. And also, as already mentioned, even among educated people, there is no clear understanding of the difference between fission and fusion, and not only in terms of physical processes that are involved, but even in very qualitative terms, what each of the two approaches can deliver. What are the costs, safety, security, energy security. So be sure that it's not controlled by a small minority of countries. What is the expected social impact? And so information is, to provide qualified information is even more necessary in a time of cultural reflux, when we risk returning to an economy largely based on fossil fuels, as we have seen in the last 2 years or last year. It is important to maintain a clear direction on decarbonization, with the project does not lend itself to invalidating criticism in terms of social costs. And one also must remember that research in fusion is not purely scientific. There are always been features from outside. And if you revisit the history of the development of nuclear fusion, one has to take into account that it has not been free of political and vested interest. The point I stressed already, probably I'm repeating myself, is the problem of control of future energy. So authoritarian regimes, at the moment you see it, are using energy supply as a weapon. And this has been quite evident in the last decade. When we have energy produced by fusion, will it be generally available or will be under a control of a limited number of power of countries or even supranational organizations, but certainly not democratic, so that energy will not be freely available, but it will still be controlled by political powers. Certainly, that would not be the dream that people had at the initial time working on fusion energy. There is a positive note that if you have that all this excitement of fusion has brought a new expansion in activities, and I'm quoting here from an important lady, a scientist who has played quite an important role in the National Ignition Facility success. And the point is that all these new activities will be an excellent opportunity to increase the diversity, equity, inclusion, and accessibility of the field of fusion, and also trying to keep or form again partnerships between private fusion companies, public universities, and national laboratories. I will stop here and thanks for your attention.
Thank you. Thank you very much, Francesco, for your very, very deep presentation. So there is really quite a lot of information and a lot to think of. And there is time for a few questions. And I can see, well, the first that is probably coming a little bit to mind, to me at least, but I can see also from the audience. And so I will start with that one. So Daniel Peters is reporting a quote that you made with possible commercial presence of fusion not earlier than 2039. And I think this is probably quite an optimistic probably date. But there are, of course, a statement from companies, private companies, and big investors to this private company. And the investor that is being cited is not less than Sam Altman of OpenAI, who has been investing quite a lot on one of the private companies, Alien, in fact, where
Yes.
they are promising to have working fusion plant or where they are much more compact. But anyway, let's say working fusion by 2028, with of course quite a lot of reduction in the cost per kilowatt hour. How would you comment to that? I think we really have all these the information that is being given contradicting what science really might be reasonably expecting, even if, of course, there is this enormous and massive investment and quite a competition from all over the world. So how would you comment to that?
Okay. First, a general observation that definitions are important. And the definition of achieving fusion is not clear. Because one thing is that you achieve in an experiment reactor the condition where you produce sufficiently more energy than the one you have to feed to it for functioning. And then may depends on your project, whatever you may think, but certainly 2028 is out of questions. And I mean, it's completely, no, it's nonsense. But possibly it could be that in 15, 20 years, people are able to realize a prototype of a reactor. It is optimistic, but it's not completely out of the question. But that you need 20 more years just to construct the large number of reactors that you need to feed the grid. So one thing is that you reach the condition where you show, okay, this is the future energy source, and we have proved that it works. It works also at a commercial level, but we have just one prototype. And then you have to construct certain number of hundreds of those prototypes. And that cannot be done in a very short time. There are construction times. That goes on the scale of 10, 20 years at least, unless maybe you put an enormous investment. But I mean, things could change. But I think it's quite dangerous from the point of view of these companies just to say that they will reach in fusion. They don't say commercial fusions very often in such a short times. It tends to confuse people. And also, you have to be careful from the point of view of the cost of energy coming from fusion, because it's very difficult, since it's almost impossible to be precise on this subject, because we still don't know exactly which kind of approach we will use. But certainly the projections that I know of produce say that in the initial phase, the cost of the kilowatt per hour from the first fusion reactors will be slightly higher, factor 2 or 3 higher, than the cost of the kilowatt from natural gas. So at the beginning, it will not be economically so viable, even from the point of view of selling this energy. Clearly, that's the difference between having few reactors in which the research and the investment costs are enormous, and then you have instead a full scale of multiple reactors, and there will be a very strong decrease in the cost of the energy produced by fusion. But this will take time. It cannot occur immediately. And I was reading also another article that stressed this point, that the first reactors will be costly. The production of energy, I mean, the cost of the energy production will be, of the kilowatt hour, will be higher than what you can get at the moment with natural gas. And that could create a kind of rejection of fusion energy from the public. So there is a transition era, sorry, that had to be addressed, knowing that it will not be so easy as these companies promise.
No, I think you're totally right. And well, something I would say similar happened also with solar energy. The cost really was quite high at the very beginning, but it halved in
Yes.
2025 because of the high production of solar panel and storage. So I think you're right when you're saying that there would be different phases. So the first, of course, we'll have really to capitalize on the research and on the investments, but then it is, of course, an incredible promise, and we will have, I think, to go down this path in order to get the energy we need.
For
So
sure.
let me go through. We already got to the hour, and I would apologize immediately to all the audience and all the people who posted questions. I will make a selection and try maybe and accumulate some of the common ones. So, a technical question, Francesco. Can you describe the sort of contamination that fusion reactor will face? Is it very different from fission?
Yes, it is. Yes, it is for a number of reasons. The point is that the amount of radioactive material, so the tritium present in a single experiment, in a single run, will be extremely small, nothing compared to the amount of fission material that you have in a nuclear reaction. So the main point that everyone stresses is that there is a major difference between fission and fusion. Fusion, if something goes wrong, it just shuts down, essentially. Fission, as we know, it doesn't. But nevertheless, in fusion, you are producing neutrons, quite energetic neutrons, and these will, in effect, make the chamber outside the plasma. For example, in a toromux, the steel chamber or the material that is protecting the steel. I mean, everything that is outside the plasma for a certain distance will become radioactive. But the difference is that there will no long terms on the scale of millennia. I mean, the materials that decay on the term time of millennia and so on. It will just be material that decay not very active, and it will decay on a time scale, I mean half time, on the scale of 100 years or less, and that it can dealt with and put aside without large problems. And also there are quite a lot of studies. I'm not an expert on this, but for example, you have to be careful that the type of steel that you use is made of components that do not bring strong, long-lived radioactive elements and so on. So the problem is there because clearly every nuclear reactor of any time, of any type, will produce some activation. But the activation that will come out from fusion reactors, from all of what we see, and from the practical point of view, is completely different and much easier than the one that comes from fission. And if I may add a point, this is also important from the development of fusion because there are some kind of regulations that apply to fissions that a number of nations, France in particular, are also applying to fusion, and that is causing some difficulties, even if actually from the point of view of nuclear activation, accident, and so on, the situation is completely different.
Thank you, Francesco. A very last question, and which is again addressing a little bit more also the political aspects. What area, private sector, public sector, or national laboratories funding the majority of the research at this time, and will this shape the direction of the commercial implementation of the fusion technology? I think you mentioned that, but maybe if you could just
Okay.
give the brief
Okay,
answer.
I think this will be a fast answer because I have the data here. At the moment, in the last year, so 2025, the total funding has been sorry, I'm trying to read total of something like $2 billion and a half, and the total public funding is around 800 millions. So you see, the public funding is much less, considerably less than the private funding. And this goes also on the overall scale that is better on fusion research. And if you need the data on these investments and so on, there is a company, Fusion Industry Association, that produce quite interesting documents. It's the one that I'm using here, when you can find all the costs from the public, from the private companies, and issue by issue on the most important private company. For example, the Trump media seems to be 6 billion.
Interesting. This is really very interesting. So I think I will stop here. And since we are already quite off of the allocated time, so I really
I'm
would
sorry I
like.
was long.
No, Francesco, it was really so interesting. And I would really like to thank you so, so much for being really with us today and giving your presentation and your insight on this very timely and very important technology for our future and the energy future. I would also like to thank all the attendees and those who are still here with us. We are still have 80 people after the hour listening to your answers. And and of course I would like to thank all the organizers and all the support that we are getting for this seminar series. It would really be impossible without the participation and the support of several people who have been organizing and supporting within the IEEE. So with that, let me thank once more Francesco and remind to all the attendees still present that the 28th of January we will have the next presentation, which is going to be again on an application of nuclear energy and in particular small modular reactors and their application to medicine. This could be quite an interesting talk because it is bridging what nuclear energy can do in very important sector like medicine and the possibility of having, of course, nuclear medicine disseminated in more than the usual regions in the world. So it is a democratization of medicine in that respect. And with that,
I may add just a sentence. If people want to get answers to the questions, they can email them to me. You can distribute my email addresses for free, and I try to answer them.
thank you. Thank you, Francesco, for your availability. So we will post your email, and I think it is even at your initial slide.
Yeah,
So that
possibly, exactly.
exactly, so people can reach you through that. With that, I close this very, very interesting session. And thanks again, everyone, for your presentation, Francesco, for your attendance, and for the support of the IEEE staff and my co-organizer. Thank you.
Thank you all.